You're sitting on a beach, watching the incoming tide carry a mermaid floating on her back up the beach. Being a math enthusiast, you record the velocity of the flow every 5 minutes for 30 minutes with results in the accompanying table. And so we, as math enthusiasts, want to know how far up the beach did the mermaid travel. And we're going to estimate the distance traveled using 6 subintervals of length 5. And we have 2 cases here. We want to use a left-hand endpoint, and then we'll use a right-hand endpoint. So before we start subdividing up this information here, let's think about the conditions we have. We again have 6 subintervals. So we want to begin by letting n be equal to 6 subintervals. And our intervals here is from 0 to 30 minutes. So we can let a to b, which we can also define as x naught to x sub n, is from 0 to 30 minutes. So in addition to this, we know that the length of each one of these, I should say subintervals, is length 5. So that's our width. So our width here, delta x, again, which is the length of that full interval, all divided by the number of subintervals. So we have 30 minus 0 divided by 6, and of course we know 30 divided by 6 is 5. And so be careful here that time is in minutes. So each interval is 5 minutes long, but also note that the velocity is meters per second. So we need to convert this width to seconds so that we don't have a conversion error. So we're going to take our width, and we know, of course, that there are 60 seconds in a minute. So we'll multiply 5 minutes by 60 seconds over 1 minute. And so the minutes units cancel each other out, and we're left, we have 5 times 60, so our width that we'll use in our computation is 300 seconds. So always be on the lookout for that. Don't let a conversion error happen to you. So the next thing that we need to do is define the subintervals. Right? And it can be helpful, particularly if you're using the right hand and left hand endpoints, given a table of values, to actually see those subintervals, to know which ones you want to pick. Is it left or is it right? So let's do this. So we have our first interval is from 0 to 5. The next interval is from 5 to 10 minutes. The third interval is from 10 minutes to 15 minutes. The fourth interval is from 15 minutes to 20 minutes. The fifth interval is from 20 to 25. And last but not least, our sixth interval is 25 to 30 minutes. So, again, this question is asking us to find the total distance. So real quick, let's just recall that distance is equal to your rate times time. So here we're trying to approximate the total distance traveled by our mermaid. So we can think about the distance being approximately equal to the change in the time, which is our width. So we have the delta x, our change in the time, multiplied by the rate. So our rate is going to be the velocity, and then we'll choose either the left or right endpoint of the velocity, depending on which case we're looking at. So this is the change in time multiplied by the sum of the velocities, the sum of those changes in rate. So we're ready for part A. And again, part A is asking us to approximate the distance. So we're going to approximate the distance using the left-hand endpoints. So if we look up at our subintervals, if we're approximating with the left-hand endpoint, that means that we're using 0, 5, 10, 15, 20, 25. We're literally using the left-hand endpoints here. So we can say that our distance is approximately equal to the width, so our delta x, multiplied by the sum of the velocities at those the left-hand endpoints. So that's velocity at 0, plus the velocity at 5, plus the velocity at 10, plus the velocity at 15, plus the velocity at 20, and last but not least, plus the velocity at 25. So we don't use the velocity at 30 because that's a right-hand endpoint. So now plugging in the given values, we know that our delta x is 300 seconds. That's the change in time. And we're going to multiply this by the sum of all those velocities. So we have 1 plus 1.5 plus 1.7 plus the velocity at 15 minutes was 1.4 plus the velocity at 20 minutes, which is 1.8 plus the velocity at 25 minutes, which is 1.6. And don't forget your units. This is meters per second. And so we can see these seconds are going to cancel each other out, which leaves us with 300 multiplied by the sum of all the velocities, which is 9 meters. And so therefore, the distance traveled by the mermaid is approximately 2,700 meters. And so this is the final answer here for the total distance traveled by the mermaid using the left-hand endpoints. And so for part B, we want to do the same thing, but this time we're going to approximate using the right-hand endpoints. So we want to approximate the total distance traveled, but this time using the right-hand endpoints. So again, looking up at our sub-intervals here, this time we want to use the right-hand side. So we're using 5, 10, 15, 20, 25, and 30. So literally using the right-hand endpoints of each sub-interval. So this gives us that the distance will be approximately equal to the change in the width, so the change in our time, multiplied by the sum of the velocities defined at the right-hand endpoints. So you have the velocity at 5 minutes, plus the velocity at 10 minutes, plus the velocity at 15 minutes, plus the velocity at 20 minutes, plus the velocity at 25, and last but not least, velocity at 30 minutes. And so plugging in the given information, we know that change in the time is 30 seconds, and we are multiplying this by 1.5 plus 1.7 plus 1.4 plus 1.8 plus 1.6 plus 2. And again, don't forget your units. That's meters per second. And we can see here, again, the seconds will cancel each other out. And so we are left with 300 multiplied, and taking the sum of all of these decimals and 2, we end up with 10 meters. And so therefore, the total distance traveled is approximately equal to 3,000 meters. Again, this is when we're using the right-hand endpoints to estimate the distance traveled by the mermaid.